Hello, happy Friday, everyone. Today I want to take a little bit of time to talk about fractional exponents, how we want to think about these things and how we interpret them when we are working on some mathematics questions. So to start off our discussion today, let's talk a little bit about what are called nth roots. And an nth root really is any real number that satisfies the equation x to the power of n is equal to a. Okay, so let's take this to be our formal definition. So in other words, we're looking for a real number. We're going to call that real number x. And that real number has to satisfy when I raise it to a certain power, I get a in return. So that's what we call an nth root of a. And just a couple examples here just to help clarify this. So let's consider the expression 7 squared. We know that 7 squared is equal to 49. So 7 is going to be a square root of 49. Now it's also true that if we take the negative, or the opposite of 7, we take negative 7 and we square that, we also get the number 49. So we also could think about negative 7 as the square root of 49 as well. Now we could go higher into higher nth roots. So typically the second root of a number like this is called the square root, and typically the third root of a number is called a cube root. So let's do an example here of a cube root. So maybe if we take the number negative 2 and we multiply it by itself 3 times, a negative times a negative times a negative, we're going to end up with negative 8. So we could say here that negative 2 is the cube root of negative 8. So hopefully that kind of gives you some idea. Maybe one last more here with the actual nth root, so a fourth root. Let's go 3 to the power of 4. We know that 3 times 3 is 9, and if we do that a couple times, we should end up with 9 times 9, which is 81. So we have 3 to the 4 is equal to 81. And we also know that if we do this with a negative 3, we should also get positive 81, because all of those negative signs will end up multiplying together to give us a positive sign overall. So those are our two fourth roots of the number 81. Now this brings up kind of an interesting quirk about our nth roots. And you'll notice here that when we're working with even kinds of nth roots, like the square root or the fourth root, it's quite possible that we have 2 of those roots. So we have the positive and the negative, or the opposite counterpart as well. However, when we're working with odd roots, like a cube root or maybe a fifth root, it's really only possible to have one of these kinds of roots. So that's something that we probably should make note of, and we'll try to explain why that is the case as well. So a couple notes here. The first one is that it's quite possible to have 2 even nth roots. And this has something to do with the multiplication of those signs. So if we think about an even number of negative signs, that's going to come out to be an overall positive number. And if we think about an even number of positive signs, that also comes out to be a positive number. So this is why it's quite possible to have two even nth roots when I'm thinking about like a fourth root or a sixth root or even the square root. However, for an odd nth root, we only ever have one possibility. And that again has something to do with the multiplication of the signs that we have. So an odd number of positive signs, of course, is going to be positive, and an odd number of negative signs is going to be negative. So there's only going to be one choice or one possibility with our odd nth roots, like the cube root or the fifth root or something like that. Now, of course, these notes really only work over the real number system. We haven't really talked about higher number systems, but there are ways to break these rules in our higher order number systems. So just be mindful that we're just working here with our typical real number system, what you guys are typically going to be seeing at elementary, middle school, or high school level. Now let's look at something that does come up every once in a while, and that is the case where we're talking about an even nth root. So here the power of x is going to be even, and the resulting number is a negative number. So a here is going to be taken to be a negative number. So let's take a look at something like x squared is equal to negative 16, right? So we're taking an even kind of power and a negative kind of a. Now, it's impossible really to solve this kind of problem because whenever we multiply two numbers together like this, either it's going to be a positive times a positive. Remember that we have to multiply the number by itself. So I have to choose a singular number. I can't kind of mix and match signs or anything like that. So I'm basically just multiplying that number by itself. And if I start out with two positive numbers, that's going to result in an overall positive number. And if I start with a negative number and I multiply those negative numbers together, again, it's going to result in an overall positive number. So kind of the key takeaway here is that x times x, this x squared, is always going to be a positive number. Right, so no matter what our choice of x is, we can never really get a negative kind of result on the right-hand side. So typically in these cases, we would just say that this equation has no solution over the real numbers. Okay, so it has no solution over the set of real numbers. It would have a solution in different number systems, but that's not the point of this little lesson here. And the last thing I want you to be mindful of is that it's quite possible to rearrange this equation a little bit to solve for x. Okay, and this is where the terminology nth root comes from. So this is x is equal to the nth root of a. So this is how we can rewrite this expression in radical form. And if we kind of zoom into this here and we look at all of the pieces inside of this little expression, we have a couple different things happening. We have the n, which is sometimes called the index. This is also called the kind of level of the root that we're working with. So in our case, the nth root. We have the radical sign. And then a here is often called the radicand. So just some terminology there for you to know about if you go doing a little bit of research in a textbook or online. And just a couple examples to go along with this particular note. If I had something like x squared is equal to 8, if I wanted to, I could rewrite that as x is equal to the square root of 8. The square root, notice, is the only root where we will not write the index. So we typically, if there's no index written, we typically take that to be a square root or an index of n equals 2. Okay, if I had something like x to the power of 5 was equal to negative 32, I could rewrite that as x is equal to negative 32 underneath the fifth root like this. Okay, so an index of 5 and the number negative 32 underneath that radical sign. Now, when we were looking at, let's say, note number 1. So looking at note number 1, it says it's possible to have two even style nth roots. So the question is, if I go to evaluate this on the calculator is probably going to give back one of those roots. The calculator doesn't really have the capacity to give back both. So give me a moment here. I'm just going to pop up the calculator so we can kind of see how the calculator's thinking about some of these particular simplifications or some of these questions. All right, so you guys should hopefully see the calculator over here. And what I'm going to do is I'm just going to pop in a square root. And let's take a number that we know we can find the square root of, like the number 25. Okay, so 25, and if I ask the calculator to simplify this, it's going to return back the number 5. Yet we know that negative 5 squared is also equal to the number 25. So why is the calculator choosing the positive number here over the negative number? Also, a couple other things to note. If you try to play around with negative numbers underneath the square root sign, obviously the calculator is going to tell you that that's not possible. So it gives you a little math error. And if you want to calculate higher order roots, we do have the cube root button. So if you hit the shift above the square root is the cube root button. So we could put in, you know, maybe 8 here, which is going to give us a cube root of 8 is equal to 2. I could also find the cube root of negative 8, for example. So remember, when it's an odd style root, we can usually find a real number that will satisfy that particular problem. And then if you want higher order roots, it's above the x to the box button. So if I go shift and I click this button over here, it kind of brings up a couple of empty spaces, and then I can put in, for example, whatever root I want to follow here. So maybe the fifth root, and I could evaluate one of the questions we had earlier, which is the fifth root of negative 32. That should come out to be negative 2. So that's how to find some of the stuff on your calculator. And yeah, if you do try to input something, like if you try to input, for example, a fourth root of a negative number, your calculator will tell you, hey, stop that. So the calculator will tell you when you run into those potential sign issues. And the reason we're getting, like I said, the reason we're getting these errors is because there's typically a sign issue. It's impossible to find a number that we can multiply by itself a certain number of even times to get that negative output that we want. So, but let's return back to the original question, which is why is the calculator choosing the positive root versus the negative root. So I know that both of them are a solution. So i.e., let's take a look at x squared. So let's take a look at the difference between x squared is equal to 16 versus actually just simplifying the square root of 16. So if I go to the calculator and I want the calculator to simplify the square root of 16, the calculator is going to be like, hey, it's going to be the number 4. But if I'm trying to solve an algebraic problem like x squared is equal to 16, well, technically there are two numbers that solve this problem. I could input I could put input positive 4 and get 4 times 4 is equal to 16. And I also could input negative 4 and get negative 4 times negative 4 is equal to 16. So I just want you to kind of understand that there's a couple different ways to phrase the problem. And what the calculator typically does is takes what we call the principal root. So it assumes that you're solving an area problem, so that the area of the square that you're working with is 16, and so the side lengths need to be a positive kind of side length. So let's just write that down. Okay, so this is a square root. So in other words, if I were to draw a square and I plot down the area equal to 16, the calculator is going to be looking at trying to figure out what is the side length of this square. The side length of this square is technically called the square root in our current day terminology. So this was kind of the old-fashioned problem that was posed by the ancient Greeks. They said, hey, what if I know the area of something? Is it possible to find the side length of something? And we talked a little bit about how to do that in an algebraic kind of way in our last class. But this is what the calculator is kind of programmed to think. It's programmed to kind of assume for these square roots or even style roots that we have an area that's a positive kind of area, so the side length is probably going to be a positive kind of side length. That doesn't really make sense to talk about area where the side lengths are negative, for example. So the positive side length is often called the principal root. Principal, so not like principal of a school where it would be P-A-L, so principal, P-L-E, and let's call it principal. In this case it's the principal square root, but principal nth root is what this is called. So typically our computers, our calculators are programmed to return the positive version of this question, and that positive version is known as the principal root. So I just want you to be mindful that, yes, there are technically two square roots to the number 16, both positive and negative 4. But typically when we're solving or simplifying square roots like this, we usually take the positive one because we're assuming that 16 represents some kind of area, and we're trying to find the side length of the square of that area. And that's called the principal nth root. So the positive side length is our principal root. That's usually what's returned back to us. Okay, so with that little introduction about nth roots, I want to essentially make a connection of nth roots back to power. So we want to try to connect our nth roots back to powers, because if I can somehow connect the square root or the cube root back to a fractional kind of power maybe, then I know all of the exponent laws. We've talked about the exponent rules before, so if I can somehow connect this idea back, then I have a whole plethora of tools that I can use to kind of figure out how to work with nth roots. So I once was volunteering at a local middle school, and I thought the teacher there had a very nice way of introducing the idea of fractional powers, and he taught the students in this kind of way. He said, what we're going to try to do today is we're going to try to determine the power of 2 that represents the square root of 2. So in other words, we're asking ourselves the question, is it possible to take the square root of 2 and rewrite it as 2 to some kind of fractional power? So we're curious about, what is it possible to do this, and what is that power going to look like? And so once he was able to frame the question, he said, well, let's just kind of assume that we can do this and see what happens. So he said, let's just assume that it's possible. And he had already been working a little bit with square roots with his class. So his class already knew that the square root of 2 times the square root of 2 should be equal to the number 2. So his class knew that already, right? And this was kind of they kind of explored this a little bit with this area problem, right? We said, if we have an area of 2 of this square, then the side lengths here must be the square root of 2. And when I multiply these 2 side lengths together, I get the area of our particular square. So he had already done a little bit of exploring to be able to develop that property of square roots. So let's roll with this idea. So let's assume that we know that root 2 times root 2 is equal to 2. And what we're going to do is we're going to rewrite these root 2's as like 2 to some power times 2 to some power. I just don't know exactly what those powers are. So we're going to rewrite So just rewrite our square root of 2 as 2 to the power of x. And I'm trying to figure out what x is. So our goal is to try to figure out what number could I put in for x to make this equation make sense. And he kind of convinced his class that if this was true, and we were allowed to use exponent properties, then the left-hand side of this equation should be 2 to the x plus x. So in other words, what we're doing is we're saying, well, I have like bases on the left-hand side, so I should be able to add those powers together. So we have like base of 2. We're going to add the powers. Okay, so we know that 2 to the x plus x is equal to 2 in this kind of made-up scenario that we've kind of dreamt up. But we know what x plus x is. We've done a little bit of work with algebra so far, so we know this is going to be 2x. And not only do we know that about the left-hand side, we know some information about the right-hand side as well. We know that this 2 by itself is really like 2 to the power of 1. We just don't typically write this number 1. And then from here, most of the students were happy kind of making an educated guess about what x should be. If the right-hand side is 2 to the power of 1, and I need the left-hand side to also be 2 to the power of 1, there's only one choice for x. X has to be equal to a half. Because 2 times 1/2 gives us 2 to the power of 1. So this was, he kind of expanded this out over the course of a few minutes, make sure that the students really understood all of the steps of this process. And then he was kind of able to conclude that if this was the case, if we started with the square root of 2 and we wanted it to make sense with all of the power laws that we have so far, then we must be able to rewrite it as 2 to the 1/2. So 2 to the 1/2 must be equal to the square root of 2. And this is true in general. So this is a rule that I would like for you to know. In general, the nth root of a number can be thought of as a to the power of 1 over n. So that is a truthful kind of thing in general. And in general, if I have a fractional kind of power like this, we can interpret this in a couple of different ways. We could interpret it as a to the m under an nth root, or we could interpret it as the nth root of a all to the power of m. And that's because of the commutativity of multiplication. So we have two different representations using nth roots. It's all dependent on the commutativity of multiplication, because I can take the fractional power m over n and I can rewrite it as, oh goodness, I can rewrite it as m times 1 over n if I wanted to, or I could write it as 1 over n times m. So I can kind of do these things in either order I want because of the commutativity of multiplication. So this is one of those kind of, I wish I had a little bit more time to kind of do some more examples with you, but I just don't. But this is something, if you do go into middle school, you want to be very, very careful with some of this stuff, because I find that this stuff is, one, a little bit hard to explain, and two, students kind of struggle a little bit with square roots. And I think it mostly has to do with their inability or their lack of want to convert these things to fractional powers, because most students aren't very comfortable with fractions either. So I think square roots are hard mostly because fractions are hard. So this is a very similar problem to algebra that we talked about, right? Sometimes, working with algebraic expressions is hard because students find working with integers quite challenging. So find the root of the problem. No pun intended. I didn't mean that was not intended, but find the root of the problem and try to address the root of the problem, right? If your students are struggling with algebra because of their integer skills, then work on their integer skills first. Get them comfortable with integers, then they can start working on the algebra expressions. Same thing here. If you run into an issue with students are kind of struggling with their nth roots or their square roots, maybe it's because they're uncomfortable converting these things to fractions and actually using fractions to do some work. So if the underlying cause is working with fractions, then you probably should be working with fractions first before you try to add something on top of that. That's always kind of my philosophy on it anyway. We won't be spending too much time with roots because we just simply don't have the time to do that. And there's some other things, some other modeling things I would like to show to you next week. So I guess for now, we'll work on one final question. I just want to give you an example of a style of question that might be on the final exam. So typically, we will have some kind of simplifying exponents kind of question. So let's just give a go to something, that's going to involve these fractional kinds of powers. And note that it's really not going to be too much different from what we were working on with integers. We just have to kind of be a little bit more careful with our work with our fractions, that's all. So let's say this should be able to be simplified to like a to some power times b to some power. And so let's try to figure out what p and q are. So I'm just going to copy down that expression, so our starting expression, and we're going to try to follow a similar procedure that we were doing for some of our other simplifications with powers. So we want to kind of look at the numerator and try to determine if I can simplify the numerator at all. Doesn't look like we can really simplify the numerator that much. All the a's are together, all the b's are together, so I can't really do much inside the numerator. So with the numerator being done, let's take a little peek at the denominator. I do notice that there are a couple expressions involving b's, so I probably can simplify the denominator a little bit. So, and what it's going to come down to is kind of looking at this root, and personally, I really dislike working with roots, so I typically favor kind of removing the roots that I have and replacing them with fractional powers. So I'm going to be taking this square root that we have, which is a squared times b, and I'm going to be rewriting it to the power 1/2. So we saw up above that we can think about the square root as a power of 1/2. So that's going to change our denominator to look something like this. Okay, so that's our first step. We're going to convert that root into this. We're going to keep the same base. So the base is, or the radicand, I guess, in this case, the radicand is a squared times b. I'm going to keep that as the base and raise it to the power of 1/2. And then from here, now that everything is expressed as a power, I can use my power laws. So I can distribute that 1/2 through the brackets over this multiplication. So in other words, I'm going to be taking this 1/2 and I'm going to be distributing that 1/2 to both of the powers. So I distribute the 1/2 to the power of a, and I also distribute the 1/2 to the power of b. That's going to essentially enable us to remove the bracket. So the second step is distributing the 1/2 through the brackets. And remember, what we're dealing with here is a power of a power scenario, so we do have to multiply these two numbers together. So we're going to get a to the 2 times 1/2, which is actually quite nice for us. So the denominator should simplify to just a. 2 times 1/2 is 1. And then we're going to get b to the 1/2 times b to the 6. So over on the side in red, I'm just going to do a little bit of work. I know I have to add these things together. So we can go kind of two ways. We can, we could make a mixed number, but mixed numbers typically aren't helpful when we're working with algebraic expressions. So my preference in this case is going to be to convert the 6 to something that has a denominator of 2. So I'm going to convert this 6 to 12 divided by 2. And then I'm going to add my units together. So I have 1/2 plus 12 more halves. That should give me 13 halves altogether. So that's going to be the new exponent that I have here for b, so 13 over 2. So that's great. That means the denominator is now as simplified as we can get, because all the a's are collected together and all the b's are collected together as well. So the next step is now to kind of look at each of these individually, each of the a's together and each of the b's together, and utilize if I am dividing like bases, I am allowed to subtract the powers. So I'm going to start with a to the 3/4, and because I am dividing by a, I can technically subtract 1 from this expression, and that's going to simplify the a's. And a similar thing can happen here with b's. Starting with my b squared, I'm going to subtract 13/2. So again, like bases means we can subtract. And I may again want to do a little bit of work over on the side, just to be a little careful with what kind of fractions I'm going to get here. So 3/4 take away 1. Well, I'm going to think about 1 as 4 divided by 4, so that I can do 3 take away 4, which is -1. So that should be the new power of a, -1/4. And let's go ahead and find the new power for b. So 2 take away 13/2. Again, not easy to do this subtraction, so let's convert 2 into 4 divided by 2. And that way we have similar units. So we have 4/2 take away 13. Goodness me, so 13 take away 4. I believe that's 9, right? So it should be -9/2. And there we go. So this is as simplified as we can get. We have all of the a's collected together, all of the b's collected together, so we know that p is equal to -1/4, and we know that q is equal to -9/2. So that's really all I wanted to show you guys. This Friday was just a little introduction to fractional powers via the root system, and how we kind of interpret some of the numbers that we're getting from our calculator, and how we might be able to explain some of this stuff to our students. So next week on Monday, we'll take a look at, we're going to be working again with some more fractions, so we're going to be doing some fractional word problems and looking at how we can model those particular word problems. And let's see, as for other kind of housekeeping things, we don't really have much to take care of. Just remember that you have the ENDA cumulative unit plan coming up here next Friday, so kind of keep on trucking away at that. I know I've received a couple of submissions so far. I'll probably start marking those once I have all of my exams prepared and ready to go. And then you have your last assessment as well. So your last video assessment is here. Just you can click on the PDF and scroll down to the Chapter 4 video assessment. These are the 2 potential videos to upload. And you can upload them right to the Dropbox when you're finished. And the rubric is attached, same rubric as the last video assessment. And the last thing is, if you would like to do a course evaluation for our course, you can go into the Moodle shell, and usually have to go into the second one, but you can go to the formative evaluation link here, clicking on the formative evaluation link and scrolling down to the bottom into the 2021 link. Will get you into the place where you can do that course evaluation if you wish. So you just have to find me. My last name starts with P. It is Penfound. There it is. So just click my name, Brian Penfound, and then we're going to click our course, which is Math 160. And then when you hit the next button, everything should populate. It shouldn't take you too long to do the course eval, but it would be nice to get a little bit of feedback from you guys about how you thought the online instruction went, because normally I would prefer to teach this kind of course in a face-to-face format where we can actually utilize some of those manipulatives together. But yeah, if you like some stuff, let me know. If you didn't like some stuff, let me know. And I will use those comments. I'll get those comments after final grades are posted, of course, and they're all anonymous. But I will use all that feedback if I were to design this course online in the future. So yeah, so it would be very helpful to get a little bit of that feedback from you guys. So otherwise, have a lovely weekend, and I will see all of you next week.